Good morning, student. Welcome to the classroom again. Last time I gave you a video clip on refraction and application of refraction. There we talk about the real depth and the apparent depth, and we equally talk of mirrorage. And we saw some application and the calculation. Today we are moving forward to look at the total internal reflection. You ask yourself, what is total internal reflection? But trust me, you are going to understand it today. Let's go to the board. Okay, if you look on the board, you'll see uses or application of total internal reflection. But before you go to the uses, you have to understand what total internal reflection is all about. Total internal reflection is a phenomenon whereby the angle of incidence is greater than the critical angle. I repeat, total internal reflection is a phenomenon whereby the angle of incidence is greater than the critical angle. For total internal reflection to occur, two conditions must be fulfilled. The first condition is the angle of incidence must be greater than the critical angle. The second condition, the light rays must be traveling from a denser to a less dense medium. When I talk of denser and a less dense medium, what do I mean? Let's take an example. If you have water and oil, if you pour oil on the water in the container, oil is going to flow. What does it mean? That water is denser than oil. That is why the oil is floating on the surface of water. Okay, we move ahead. We look at the first use of total internal reflection. Total reflecting prism. We're going to look at its use in total reflecting prism. We have an instrument known as a periscope. This instrument is used to see around a corner. For example, you are in front of a door. I want to see what is happening inside the house. You don't need to bend. You just need a periscope. You place one end on the floor and you stand and look. It's going to give you all the information of what is happening inside the house. That instrument is known as a periscope. And it works based on the principle of total internal reflection. You can see the diagram on the board. Assuming that you are here, this is your eye. You want to see something's happening in the house. You hold your periscope. What is happening in the house? Rays from object. Here you stand, you put your eye here. The ray will come here. When you meet this prism, the ray A is going to hit the prism here, and ray B is going to hit the prism here. This ray is totally reflected. It goes up. When you meet this other prism, it's going to reflect, comes like this, and come like this. This is what we know as total internal reflection. Or other way, or in the other hand, if you are standing here and you want to see an object, you place and you stand. You want to see an object inside the house. You stand here, you are looking in this direction. This way you are. Rays are coming like this. We hit this prism, it comes down, it comes down, and it moves inside. And therefore you can see any object or whatsoever is happening inside the room. We call this object the periscope. Okay, we move to the second use of total internal reflection. We talk of optic fiber. Optic fiber is what has modernized our society today. Without optic fiber, our internet will be slow. Without optic fiber, we have slow communication and transmission of information. And therefore we use optic fiber in communication, in medicines and internal surgery. This is due to what? Total internal reflection. Optic fiber has a very great advantage as far as communication is concerned. It has great advantage over cables. For example, optic fiber carries a lot of information compared to cables or wires. Equally, optic fiber is very fast as far as communication is concerned, and equally have optic fiber there's a little or no loss, there's little loss of energy as far information count is concerned. Therefore, the energy loss along the way is minimized. That is why nowadays we prefer optic fiber to wire or cables. Okay, here we are going to see some exercises on how to calculate refraction of light, because you must be able to calculate refraction of light. You must be able to also explain your answer as far as the calculation is concerned. Okay, we move to the first exercise and then we see what is going to happen. Okay, the first exercise, we have a student standing at the edge of a swimming pool sees the bottom of the pool and concludes that it is exactly 3 meters below the water surface. Draw a label ray diagram which shows that the pool is deeper than 3 meters. B. Which common property of waves account for your diagram above? C. If the refractive index of water is 1.3, calculate the true depth of the pool. Okay, you realize that in most cases when we stand in front of a pool, a swimming pool, and you are looking at the bottom, it seems as if the bottom is closer to the surface. It is not like that. But if you send your hand keeps on going deeper, deeper, and deeper. That is why you can make an error and drown in a swimming pool because of your imagination. You should know that when you stand beside the swimming pool and you're looking at the swimming pool, what you are seeing as the bottom is not the actual depth of the swimming pool. And therefore we are going to do this calculation whereby we are going to draw a ray diagram to show you what is happening. Okay, I go this way. Okay, let's start by solving the A part, which says to draw the ray diagram. This is a swimming pool, and here we have water molecules. Here we have water molecules. Okay, this is the real depth of water here. This is what we call the apparent depth here. Okay, I draw a ray diagram. I want to draw my ray diagram. Let's say something like this. Remember, I draw something like that. I call it draw something like this. Good. I take care from the bottom here. Okay, I call it take here. Here, this is your eye. This is your eye here. The ray is coming like this. The ray is coming like this, and this is water body. You can see here, this is the actual depth or the bottom of the swimming pool. But when you stand beside the swimming pool, looking at the swimming pool, it seems as if the bottom is rather above or closer to the surface. Therefore, we call this point here. I want to label this point here. The distance from here, the distance from this point to this point is called the apparent depth. We call the apparent depth. And the distance from here up to the bottom, we call the real. We call the real or the true. The real or the true depth. Okay, that is a ray diagram of what is required of us to draw a level ray diagram which shows the pool is deeper than 3 meters. Okay, this is a real depth. We see the real depth, it shows, but means that the apparent depth here is 3 meters. The distance from here, you are seeing it as if it is 3 meters. Actually, it's not 3 meters. And then this is why we are asked to calculate the real depth. Let's call it X. Good. Let's call the actual or the true depth X. Okay, we go to the B part, which says, which common property of waves account for your diagram above? The property is refraction. The property here is refraction. It's refraction that account for this effect. Therefore, this is A, and the B, the property here we have refraction. It's refraction of light. And the C part, we are asked to calculate if the refractive index of water is 1.3. N equals to 1.3. And then the apparent depth, the apparent depth, we are given apparent depth as 3 meters. And the real depth, the real or the true depth, we are given, let's call it X. Now you are asked to calculate the true depth or the real depth of that pool. I use my formula, refractive index N equals to real depth divided by apparent depth. This is the formula. Refractive index N equals to real depth all over apparent depth. Remember, our refractive index is 1.3. Of 1.3 equals to the real depth. We let our real depth to be X. X divided by our apparent depth. We have it as 3 meters. We have 3 meters. Good. Now, if you cross multiply, I can put down I can say right as 1.3 on 1. If you cross multiply 1 times X, that is, we cross multiply. 1 times X is X equals to 1.3 times 3 meters. 1.3 times 3 meters. Okay, if you take 1.3 times 3, use a calculator. If you take 3.9 times 3, we are going to have 3.9. Implies that our X here, we are going to have 3.9 meters. It therefore means that the actual depth of that pool is 3.9 meters. But we were seeing it as 3 meters, which is not correct. The actual depth is 3.9 meters. Dear students, we have come to the end of our lesson. And what we have just done, I believe that you're listening, you go to your textbook, you equally find similar exercises and you solve. I will equally send you exercises on the website where you are going to send and submit to me in due time. I therefore urge you, go for further study, and any challenge, don't hesitate to tell us for us to help you. Thank you very much.